All right. Cool. So, reminder, check out that video. It's in the content area. I made a new folder, videos, and it's all the numbers with Trey Parker. It's amazing. And and even more amazing, there's my notes. I hid them. So let's just see. I had an idea of what we wanted to talk about. Let's keep rolling. What I'm hoping is to get through about an hour's worth of stuff today. Give you about 15 minutes to look at the homework if you haven't yet. I kind of hope you have, but I don't want to know if you haven't. So I'm extending the due date to next Friday, first off, because I forgot we don't meet on Monday. But start beforehand, right? Like you really want to just start on it beforehand. So let's get that first little bit of news up here. So homework 1 is due next Friday, and let's put a due time, let's say by 1 p.m. You can just drop it in my box. I'll be in like 12:30, but if you could drop it there by 1, that'd be great. I'll be leaving my office at 2. If it's not to me by 2, then it's like, why are you doing this? Just get me something. You'll get to fix it if it's not ideal. So I think last time we talked about the natural numbers, and then we talked about ratios. Oh, got one in here. When we talked about extending that to the positive and negatives, closed under addition and subtraction. If we want to close that under, they're also closed under multiplication, but as soon as we want to have the inverse operation of multiplication, aka division, we have to move up to a new, what's called a field. And a field is kind of like, has all the great properties of number systems that you want. It allows you to take inverses. It does all the things you want to do with arithmetic. These are not fields simply because they have that additive closure, and they have additive this doesn't have additive inverses. But this you can plus and minus, but you can't divide. Here you can plus, minus, and divide, and everything lands back in that group, that set itself. So if you, how many have had abstract already? So if you had abstract, there's the idea of a group. This is a group under addition because it has it's closed under addition. You have inverses. This is got like 2 group structures on it. It's got the group structure of addition, so you got plus and minus, and it's closed under those. But it's also got this other group structure, multiplication. So, and they're all put together, and then they link together in ways like this, the distributive property, where you've got plus here, you've got times here, and things work out to be able to distribute like you like to do. So this is kind of the lowest order field that we have. Mathematicians really like to name things after natural objects. I want to spend a little time on this today, and in the course of talking about this, we're going to progress to the full real number set. So I'll let you know that like here there's going to be the real numbers as kind of our maximal collection of numbers we're going to talk about. And again, check out Trey's video on all the numbers to see how little we actually know about this. It's crazy. It's actually pretty cool. Like already, my mind is digressing down videos I watched about math yesterday, so I'm going to try to like pull it back in here. So let's talk about this. So Cecil had given me the example. I was asking for examples of numbers that weren't rational, and Cecil had said 0.6 repeating. So let's just take a look at repeating decimals. And I think at the end of the hour, I made the note that, oh wait, that's 2/3, and Cecil was like, yeah, of course it is. I just, wasn't thinking that, just thinking of a lot of digits here. So anytime you have a repeating decimal, let me show you the trick. for converting it to its rational form. Does anybody know this already? The trick where you get a repeating decimal and you can convert it into a fraction? Have you seen this? Yeah, Cormac, you've seen it?
I don't remember that.
Yeah, okay, cool. Nobody remembers exactly how to do it. Okay, cool. Most of you don't, so it's worth talking about. So let's see, it's what is the date? It's, what is today? It's 1/15/2025. So let's make that a repeating decimal. Let's make it 11.52025. 52025. 52025. Forever and ever. So it's repeating. And it's got this like whole part out front, unlike this was purely fractional. But the fact that this is repeating, I know because I know this trick, I can convert that into a fraction. And here's how to do it. Let this be a number x. And then we're going to multiply x by the number of spaces we need to move the decimal point to get this repeating part to line back up. So in other words, if I move this decimal place 1, 2, 3, 4, 5 spots, then notice how this repeating part lines up with the original repeating part. So let's see, so that's 10 to the 5th. I need to roll it, so 10 to the 5th, we'll just put that here, x equals, and I'm gonna write what that turned out to be. It's 11.52025.52025, blah, blah, blah. So let's take a look, just make sure you're with me. Just wanted to shift this thing over so I had all the repeating stuff. And 10 to the 5th, what is that? That's like 100,000, something like that. Is that 100,000? Yeah, that's 100,000. So this is actually 100,000. And what I'm going to do now is subtract these two. Think about what's going to happen when I subtract. The repeating parts are going to cancel out completely. You just get a 0.0 after that. So I'm going to get here 99,999x equals whatever 11.52025 minus 11 is. That's actually not too bad. That's 11.52014.0. Check my math, please. Let me know if that looks good. So the goal is to just multiply the thing you've got by enough powers of 10 to get this subtraction to cancel out the repeating decimal part. And then you just solve for x. So x is 1152014 over 99999. Done. And if you kept your calculator out, does anybody got calculators? Oh, you got a phone, we got calculators. Let's just check that out. If you could just do that division and see if you get 11.52025, that would be great. This tea got made in a weird cup. I'm a little worried about drinking it today. I feel like I made it in a garbage bin. Like seriously, I have these like old cups sitting around my office. Accidentally made it, the old one realized that was chunky. That was scary. Chunky tea. I remember somebody in my family once made tea in a cup that some dog teeth had been kept in. And then didn't realize it till they started drinking it and got one of the teeth like in their mouth. I don't think I'm that bad off. I haven't lost any teeth in my office. No one else has either. How'd that turn out, that division? Yeah, checked out, cool. So now you know that trick, and now you could convert anything. So let's say I didn't know this was 2/3. Here I just got to multiply by 10. Subtract. Oh, look at that. Needs a little simplification, but it's 2/3. So, cool. So repeating decimals are not irrational numbers. That's one thing to just keep in mind. Keep that in mind. And we talked about some examples of some rational numbers. I think square root of 2, square root of 3, pi, e. These are all classic irrational numbers. And I don't know if I mentioned or not, but either pi times e or pi plus e is irrational. Did I mention that? Because I don't think I did, but I wanted to. We don't know which one is. We simply know, like, isn't this crazy? We just know one of these must be irrational. Someone proved that, but we don't know which one. And that's just weird. We also know that pi to the e, this is irrational. That's been proved. And you'll see some of this in Trey's video. I think he even references this fact. But we don't know if this is irrational. We don't know. I think we might not know if pi to the pi is irrational either. Just so many simple things. Like, that seems so simple. How can we not know that? Well, we don't. No one has proven it yet. They might, and to prove, you literally have to do a nice, beautiful math proof to get that. You can't look at a computer output of the decimals because you never know if it's going to repeat again. It might repeat at the 10,000th place or the billionth place. We don't know. So, a lot of undiscovered things if you're ever looking for an adventure. There's more fruitful things to do in this life than work on that. But, I'm not going to stop you from chasing your passion at all. Let's talk about a way to see if a number, certain kinds of numbers are irrational or not. And actually, what I kind of want to do to get you there is to give you a couple of proofs that square root of 2 is not rational. So let me show you the classic proof, and then the way our book does it is something I'd never actually seen before. And it gave me a few questions, but I think it's a cool proof, and it's the way I want you to proceed in your homework, because this method is weird. So here's just a quick proof claim. Oh my God. Claim, oh please, oh boy. I don't think I have my bag. Oh yeah, there we go. Claim square root of 2 is irrational. So I'm gonna show you the old school proof, and then we'll look at I don't know how new school it is. I mean, all this math is like freaking 100 years old plus, but it's old, it's newer than the pyramids. So we got that going for us. So the proof, I'm going to proceed by contradiction. So you get to see a little, I'm also trying to review methods of proof. Proceed by contradiction. And what that means is I'm going to assume square root of 2 is rational and wind up with two things that collide and can't both be true. Does this sound familiar? Everybody's on this method of proof? Cool. So proceed by contradiction, i.e. assume that the square root of 2 is rational. And what does that mean? That means, i.e. square root of 2 is equal to some a over b. So I can write it as a fraction, and a and b are whole numbers, where a and b are integers. We know b can't be 0. And let's also assume, remember when we came up with 0.6666 was this? That wasn't in simplest form. We could actually write that in simplest form. Let's assume that's in its simplest form. So we canceled out common multiples and stuff. And a and b have no common factors. Everything sound good so far? You with me? And then we're gonna wind up with a contradiction of something that we've assumed here. And just a hint, it's going to be this. This is the thing we're going to collide with this no common factors claim. So you can see it coming and ahead of time. So I'm going to take this statement and I'm going to square both sides. And I get 2 equals a squared over b squared. And then I'm going to multiply both sides by b squared. And we get that relationship. And this is the subtle move right here. And if you don't believe me, and I can see why you might not, tell me that this isn't, you're not quite sure you believe this. But what we've done is we've kind of taken this number a squared and we've done a factorization, started a factorization over here. So this statement right here means that a squared must be divisible by 2 because 2 is a factor. So I'm going to write that up. So this means that a squared must be divisible by 2. But the only way, so here's the subtle part, the only way that can happen is if a is divisible by 2. So let's think about this. Now, let me get there another way. What if I had said, you don't write this down, but what if I had said to you, a squared is divisible by 4? Then it's possible that a is divisible by 2, and since I've got a times a, the whole thing could be divisible by 4. So 2 could, if I say this, that means 2 could be a factor of a itself. But as soon as I come down to a squared is divisible by 2, that would mean that only one of these could be divisible by 2. Or if it's divisible by 2, both of them must be divisible by 2. So I can't just have one of these divisible by 2 and the other one not divisible by 2. And that's because 2 is a prime number. Do you see what I'm getting at here? So let me write it out and maybe it'll make a little bit more sense. So a squared must be divisible by 2. Therefore, a itself must be divisible by 2. Look at that. Think that out. Just make sure you believe that. And if you don't, seriously, that's what we're here to talk about. There's going to be a lot of stuff that happens in this class that is not believable. And let's just make sure we're honest with each other. And you let me know. And it's because 2 is prime. Let me show you again let me show you, if you don't quite believe that, what if I said a squared must be, let's see. Yeah, I don't know. Do you believe that? I don't want to keep saying stuff about it because yeah, does it seem reasonable? Okay. So a itself must be divisible by 2. Therefore, a must equal 2 times some other number k. So a is 2 times something. So that means that a squared must be 4 times k squared. So let's take a look. Check that out. So since a must be divisible by 2 because of that relationship, a has to equal 2 times some other number. And now I'm going to take this relationship here and rewrite it. So star becomes 2b squared equals 4k squared. See how I got that? It's cool. And everybody's nodding for the most part. And that is cool. But I just want to let's not play that nod game just to appease me and get me off your case. Let's be real with each other. So let me know. Okay, I want to believe your nods when I see them. And I'll be okay if you don't. I'd rather have you tell me. So look, divide both sides by 2. So b squared is 2k squared. So let me ask you something now. What do I know about b itself? Well, what is it, Corbett? Yeah.
It must be divisible by 2.
So in the same way that yes, exactly. In the same way that this relationship said that a must be divisible by 2, now we see b squared has 2 as a factor. And that can only mean that b itself has 2 as a factor, because it's b times b. It's the same thing times the same thing. So this means, therefore, b is a multiple of 2. Exclamation point. I'm super stoked. Why? Why am I stoked, Cormac?
Because a and b have no common factors.
And now we just showed they had to, right? So see now, yeah, since they're both even, we didn't get this thing in simplest form. So, but we assumed a and b had no common factors, and now we've arrived at a contradiction. And so that the way you put that in proof is C exclamation point. At least that's the way we did it in the old days. That means contradiction being screamed from the tops of the mountains. Therefore, our original assumption is false, that square root of 2 cannot be written as a fraction. Therefore, square root of 2 cannot be rational. And that, there you go, my friends, that is a classic proof. You can do that with square root of 3, square root of 5, any of those nice primes like that. Same, with exactly the same reason. You can show square root of 5 is not rational, is irrational in the same way. So then let's talk, let me give you a minute to process that, and I'll show you the alternate proof, but we got to talk about a theorem first. And hopefully you did the reading. Look at the floor. Walk around. And you are totally, when I say the rational zero theorem, you're like, yeah, oh yeah. Totally so. Yeah, that's the way. That's the look. Yeah. Can I erase this left side? Cool. So the rational zero theorem, I'm not going to go through the proof. That would be something you can read on your own. That would be mind-numbing. It's kind of a boring proof. But let's look at the result. So the rational zero theorem. And like I said, I've never seen this proof method. I knew this theorem, and we probably all did at some point in our life. It says that if I have a polynomial, an nth degree polynomial, set equal to 0, oh, plus a naught, I've got a constant term. So if I'm trying to find the roots of a polynomial, then every rational solution has a certain form, and the form is this. X is equal to plus or minus a factor of the constant term over a factor of the leading term. And we'll do a quick example just to make sure we believe that. So, do a little sneaky work over here. Okay, so example. If if I gave you this equation to solve, and we're looking to see if it has any rational solutions at all. First thing I would do is look at all the possible rational solutions. And those are going to look like this. They're going to be plus or minus a factor of 3, and I could say negative 3, but I'm putting plus or minus here, so we got it covered. Plus or minus a factor of 3 over a factor of 2. And then you get really pretty much filled with joy, because there's only 2 factors of each of those numbers, right? So i.e. plus or minus 1 or 3 over 1 or 2. And I make a list of all the possible things. And so I come through here and I say, okay, so the rational, so this is equal to the set. Let's do 1 as the denominator first. So it's either plus or minus 1, plus or minus 3. That's when 1's the denominator. Or plus or minus, I'm going to use 2 as the denominator now, 1/2 plus or minus 3/2. And so if anything, any rational solution exists, it's got to be one of those. And then we whittle it down. Now, I'm not going to go through the process of showing you how to do synthetic. I don't want to, God, we could talk about, just so like, how do you check if you're interested and you don't know? I highly recommend you learning something about synthetic division to see. There's also like all sorts of weird things that I don't even know if people learn anymore, like Descartes' rule of signs, like how many positive roots there must be, how many negative roots. And you look for sign changes. So here's plus 1. There's only 1 sign change, so there can only be 1 positive root. And so this, I'm using Descartes' rule of signs. Look these things up. And it's pretty easy. Descartes' rule of signs is literally look for how many sign changes there are in the polynomial. And then you change all the odd powers to negatives and look for the number of sign changes after that. So there's only 1 sign change when I do that. So there's only there's 1 negative root, which is cool. Now I know 1's positive and 1's negative. And that would help me at least narrow things down. Now the polynomial that I secretly wrote over here, I hope to God, well, let's just go ahead and factor it, because this one's at least just quadratic. So I used a 2x and an x, and then I had a 3 and a 1, and I'm pretty sure it was plus and minus, yeah. So this was the polynomial I multiplied out over here in secret. So the roots are actually x equals 1/2 and x equals -3. These are our roots. And they definitely occur in the list. So how do we use that to show that a number is irrational? And this is fun. This is actually kind of cool. So, show. We're going to use that result. Show, let's see, I got a new funky one here. 3 plus the square root of 5 to the 1/3 is irrational. So what we're going to do is we're going to create a polynomial that this is the solution for, a solution for. And then we're going to use the rational zeros theorem to show what are all the rational zeros. And if this doesn't show up in the list, it can't be one of them. That's the game. So let's do this. So, proof. I'll kind of outline this here. We create a polynomial for which x equals 3 plus root 5 to the 1/3 is a root, and show that this number, that x isn't in the list of possible rational roots, isn't a possible rational root. That's the game. This is one of your homework problems. You got one like this. So just take this equation here. You're going to say, okay, so I'm letting x equal 3 plus root 5 to the 1/3. And now I just kind of need to undo this. What do you think might be a good first move toward getting a polynomial from this? What do you think's a good first? Like, I don't know. What does it kind of make you want to do to both sides?
The cube root.
Yeah, take the cube. Let's cube both sides. At least get that nasty cube root off there, right? So I'm going to cube both sides. Already better. Let me give you another hint. The square root of 5 over here, I'm going to want to square that out because I want to get all, I guess what I should have said over here is that these not A1, I forgot to say this, through A sub n are integers. They're whole numbers. Actually, sorry, yeah, they're integers. Yep. So I'm looking to get an equation that's got, I don't want a square root of 5 as one of my coefficients, is what I'm saying. So what I'm going to do next is subtract 3 from each side. And then I'm going to square each side. So let's see here, cube, subtract 3, and then square, again, or squared first time. So I've got x cubed minus 3 squared equals 5. Pretty much almost home. Seem okay? Make sure you're cool with what's going on. I don't know why this feels so satisfying to me, but it really does. So I'm going to FOIL this out. So this is expand left-hand side, move the 5 over, and get an equation equals 0. So x to the 9th minus 6x to the 6th plus 4 equals 0. And then I ask you, friends, make a list of all the possible rational zeros of this equation. What are they? And make it like this. Olivia, you think you got a list?
Not yet.
Okay. If you already got a list, I'm going to ask you, how do you know your number isn't just one of those numbers in disguise? Think about that if you already got your list. Cecil, you got a list for me?
Not yet.
Not yet? Okay. If you have that, who actually has a list? Cool. So how do you, so you've got 2 in your list probably. How do you know that number isn't equal to 2? Square roots and cube roots mixing together, who knows? I mean, without a calculator, right? We're not gonna get a calculator out. Can't trust that calculator anyway. Camila, do you have a list? What you got, friend?
Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 2/3.
Ooh, how'd you get 2/3? So we've got all the factors of 4, which are, so that I was with you on that one, right? All those.
And then the factors of 9, right?
Ah, the
Oh,
leading
okay.
coefficient. Okay,
Okay,
cool,
okay,
cool,
yeah.
cool. And maybe that's what's slowing some other folks down, because that's a shitload of rational zeros. It's that leading coefficient. I'm glad we had that conversation. Yeah, I wasn't trying to be too mean. Yeah. There we go. Does that feel better? Okay, cool, awesome. So this is literally our whole list right here. There's only 6 possible rational roots. And it looks like that's not in the list, right? Like I look at that, and I mean, I could get my calculator out and see that there's no freaking way that's in that list. But what if it was? And I'm not going to ask you to do this in your proofs, but I kind of, it's a question that bugged me when I was reading this proof. I was like, well, okay, but how do I know that's not one of those numbers? So let's actually kind of rule out some of those numbers. First off, I think we could probably safely rule out the negatives. Yeah? That's because I've got a positive plus a positive, and I'm taking the cube root. I know that this quantity is positive. So I could definitely rule out all the negatives. So the only thing, so I'm just going to put this up here. How do I know this isn't 1, 2, or 4? Don't do this in your proof for your homework, but it's something that we should talk about because it really bugged me. Any ideas? Because I did this on my own because I was like, I had to convince myself that it wasn't.
You set like cube root of 3 plus 5 equal to like any one of those.
Yeah, that's a dang good route, definitely. We could rule out a few things in that 3 plus square root of 5 is definitely bigger than 3. So its cube root is definitely bigger than 1. Because the cube root of 1 is 1, and then it just moves up from there. So I could rule out 1 kind of that way. And in a similar way, I could say that 3 plus square root of 5 is definitely less than 64. Like that's not a crazy thing. That seems pretty clear. Square root of 5 is less than the square root of 9. That's just 3. That's less than 5 over there. So it's definitely less than 4. Its cube root is less than 4. So the only one that might be dicey here is 2. So let's just set this equal to 2 and the cube root, yeah, and just see what happens. And so I just unfolded this. Then I almost did what we did here. I cubed both sides. If this is true, then this would be true. And then that, if you subtract 3 from both sides, we get that, and we know that that's a lie. So, just if that question had come into your mind ever, don't worry about it. You're gonna be all right. So I think that's a cool way to proceed. Now you know a couple ways to show a number is rational. The numbers that we're talking about here are a very special category of number, though. And I just want to make sure you couldn't use this for pi. You couldn't use this for e because they're different than this number. Let's just talk about this. Any number that is a root of a polynomial with integer coefficients is called algebraic. We don't have a set, but I kind of want to just make up a notation for it and call that fancy A for the algebraic numbers. Never seen that before. That's non-standard notation. I'm just calling it that. Any number that's the root of a polynomial with integer coefficients we're going to call it algebraic. So pi and e are not algebraic because there is no polynomial of that form they are roots of. So like this method won't work for that. These are, any number that isn't algebraic is called transcendental. And that's just awesome. Cool word. Transcendental numbers. So they're not algebraic. But they are irrational. Not all of these are irrational. For example, here's a polynomial. Root of that is 2. That is a rational number. So these algebraic kind of sit across. So if we had the natural numbers, and then we had the integers, so I'm doing Venn diagrams here, and then I had the rationals here. The transcendental numbers are out here. So transcendental numbers are somewhere out here. They don't fill up the whole space, and that's why I want you to watch Trey's video. So get into this. Transcendental numbers are out here, but and maybe they are the whole. I don't know. Watch that video. I'll have to watch it again too. But the algebraic numbers, and then there's the irrationals are out here. Yeah. So like there's transcendentals and irrationals, and they're kind of mixed. There's a mix out here of those two kinds of numbers, and then there's the algebraic numbers that come inside this set like this, and this is just the algebraic numbers. Whatever that spillover is out here into that region of irrationals, the algebraic numbers kind of make a little subset out there. They're closed off from everything else. Never made that picture before. That might be total bullshit. Seems right. Seems okay. How you feeling? Everybody good? Just a little variety in the sound besides my crazed voice that inevitably sounds sleepy. All right, I got one last thing I want to talk about. That is absolute value, because honestly, you're going to get to know the absolute value. So, but before we even go there, let's just look at our final picture. Here's the real number line. Real line. This is a mix of the rationals and irrationals. So together, the rationals union with the irrationals make up the real numbers. But they are tangled in such a crazy way that we can't draw the picture of it, but we can explore it, and this is what we're going to do for a while. We're going to do this in great detail. So in here, there's I've got a couple rational numbers. I've got like a rational number here, and then I've got a rational number here. And no matter how close they are, there's another rational number between them. I'll just take the average. And no matter how close they are, there's an irrational number between them. So this thing is weird. If you wanted to draw, and one thing I'll tell you here, and we'll see this a little bit later, there are infinitely less rationals than there are irrationals. These things we can make a list of. I can like literally list out, and I'll show you, it sounds weird, but we can make a list of all these. These cannot be listed. There is a countable infinity of these. There is an uncountable infinity of these. Uncountable infinity is so much more infinity than countable that it's like dust versus solid. How many folks have at least seen some stuff with countable versus uncountable? Yeah, a little bit, yeah. We'll get into it. We'll do some of that. That's not for today. I kind of want to just wrap up today talking about that, but I want you to start like seeing the magic and the crazy mind-bending structure of just this freaking line that you've just taken for granted. What's going on in there is beyond comprehension. It really is. So, with that little teaser for what's to come, honestly, real analysis is, a lot of it is making sense of this and gaining a vision and a way to think about that. We're going to get in there with our mathematical microscope and understand better. So let's just talk about absolute value, because you really need to know more about that than you've ever known in your whole career as a mathematician student. Absolute value, sounds simple. So let's take a real number A. Anybody got a definition for absolute value? What have you used? There's a couple ways to do this. Yeah, what you got?
Distance from zero.
Say it again.
Distance from
Ooh,
zero.
I love that. Yeah. Distance from zero. And the kind of underlying assumption here is that distance is a positive quantity. So positive, or a non-negative quantity. Non-negative distance. So let's just do, I like that, thank you. And in fact, that ties in really well with something that we're going to talk about and is in our book. So if I said, what's the absolute value of -3, using Camilla's definition, it's this distance here, which is 3 units. That's nice. That's a super intuitive way. I love that. And we'll keep that as our primal definition. It's a great one. You can picture it. Another one, anybody got another one for me? Anybody got piecewise one for me? What if the number that I'm taking the absolute value of is non-negative? What does this return? Absolute value of 7 is what? 7. Absolute value of 0 is 0. And use Camilla's definition to gain intuition about that. So if I say I have a number here and it's not negative, just spit that number back out. What if that number is negative? What if I said absolute value of -3? How could I compute what comes out? Give me a formula for 3. How do I convert -3 to 3? Don't get too fancy. Multiply by -1, take the opposite of it. So it's actually -3. So we'll say spit out -a if a is less than 0. And we have a nice rule, we could program this. If we program this, the computer has to understand distance. To understand distance, we probably have to teach it this. There's one more that we're not going to use because I like to use it in calculus. So this is more of a calculus definition if I wanted to take a derivative or something, but it's the square root of a squared. First you square it, that loses the sign information, then you take the positive square root. I'm not putting a plus minus up front, just taking the positive one. So you can use this to take the derivative of absolute value if you so chose. anywhere but at 0, where it's not differentiable. All right, so key results about this. And you will surely go back and again read that stuff I asked you to read. But then you'll finish reading the whole first section and you'll read up through absolute value, please. Yeah, you'll do that. That is literally up through. Don't cheat yourself on this stuff. This is up through page 18. Let's take a look at some of the key results about absolute value. I'm not going to prove all these because that's super boring. I'm going to show you some tricks. So theorem 3.5 says the following, that the absolute value of A is greater than, it says 3 things. The first one is this, for all real numbers. The proof of that is kind of obvious in a way. But if you think about Camila's definition, it's definitely, we've literally defined it to be a non-negative thing. But mathematicians being mathematicians, here's a proof. You don't believe it? You want to get tedious? Math's for you. I guess that's why you're here. 2. The product of 2 numbers, the absolute value of the product is the product of the absolute values. And again, I just want to check, this notation cool with everybody, or should I explain it? It's been a while. Cecil, you good on that notation? Yeah. Does anyone ever call you Livy?
Yeah.
Do you like that?
Yeah.
What do you prefer?
Because
Like I keep in my brain, I keep like thinking Livy.
Yeah, my family calls me Libby.
Okay, well I won't like step over that.
You can if you want, I don't care.
Can I?
Yeah, sure.
Okay, cool, thanks. Cool, because that's like what my brain wants to do.
Yeah, my family calls me Libby. A lot of my friends call me Liv.
Live?
Mm-hmm.
Cool. Oh, that if I slip into that, forgive me. I'm a 1-syllable kind of guy. It just like.
That's what all my friends are like. Liv. It's easier.
Ooh, and nice. Okay, thank you. Thanks for the permission. Yeah, awesome. Yeah, yesterday I was like watching, Olivia Newton-John was like my first crush. My first like celebrity crush. You guys are too young for that, but I was watching this video of her singing this song. I like got super emotional. I just love her so much. Well, she's gone now, but what a beautiful lady. Okay, well that's enough of that weird talk. This is the one I really wanted to talk about, and I kind of introduced this last time. This is probably one of the most important things that we've learned so far. That's the triangle inequality. And good God, you're going to use that so freaking many times. Like seriously, this result, if anything you come out of this class with, it'll be that. This is the triangle inequality. And there again is a proof that I'm not going to give you. But I can intuit a proof. We can intuit that this might be true. If A and B are both positive numbers, then A plus B is a positive number. And this is just normal addition. This gets bigger. If it's 3 plus 5, that turns into 8. And if I take the absolute value of a positive number, I just get 3 plus 5. So if A and B are the same sign, if they're both positive or they're both negative, that's where I get equality. If one of them is the opposite of the other, or one's positive, one's negative, then you're making things less. You're subtracting from one of them. And that makes this distance smaller. So that distance here would be smaller than the cumulative distances. So for example, if I had 3 minus 5, that is clearly less than the sum of the absolute values. So just keep in mind, this less than kicks in when these are opposite sign, just to like understand this thing from a more intuitive level. So on its surface, it seems pretty natural. But there's some things that come from this that aren't as natural. And there's a trick that I want to show you. And I want to go to Camila's talk about distance. And we can see something here. So let's go to that definition. Definition. And we're going to kick in that triangle inequality. Definition. For A and B that are real numbers. Let's draw. Let's see. Oop, I don't know why I got that so crazy. There's 0, let's say there's B, let's say there's A. Maybe they're just like on totally opposite sides of 0. So that thing I was talking about over there. Define the distance from A to B. The distance between these two numbers to be the absolute value of their difference. So think B minus A is this quantity right here. But one of these, it could be the other way, right? I could also be taking, I could have, if I do B minus A, it might have been that B was over here and A was over here. So since this is a fixed thing, B minus A here would be positive, but here B minus A would be negative. But it's still this distance here, it's just the negative of it. It's that difference. So I want distance to be positive, as Camila offered to us, and I confirmed. So this thing right here is always greater than or equal to 0. What's the distance between, I don't know what it was, let's say 7 and 2. Absolute value of 7 minus 2 is 5. I could have done that. Notice how distance from A to B is equal to the distance from B to A as well. It's a symmetric relationship because of that absolute value. So you got that, you can't go wrong with it. So this is equal to the distance from 2 to 7. How did we get so far knowing each other and now I just know that?
I was thinking that too. I was like, I should have told you that like
Yeah,
4
it's
years
crazy.
ago.
It's just crazy. Yeah, it's all right. We're here now. So one cool relationship and an important trick. So this and the trick we're about to see are like half of real analysis. Yeah, I don't know. Half might be an exaggeration. So we have this theorem. For A, B, and C that are real numbers, the distance from A to B plus the distance from B to C is greater than or equal to the distance from A to B. Draw a picture. Sorry, this should say A to C, excuse me, sorry. I saw my picture up there, I got it right. B is the common thing here. So if I have the distance from A to B, right here, and the distance from B to C, right here, that is greater than or equal to this distance right here. So this is distance from A to C, and here this is distance A to B, this is distance B to C. And in the picture, the way I drew it, we actually have equality. This length plus this length is clearly this length. Does that sound right? Yeah, you can add those together. So when it gets weird is if that B is outside the range. So if I had B out here, A and C, this is where the inequality is going to happen. So here we have distance from A to B is this. Distance from B to C is that. And that sum plus that sum is clearly bigger than that distance right there. So here's where we got inequality, here's where we have equality. Just a little example of how that could happen. I'm going to prove this because the proof has got the trick that you're going to use all the time. When we start getting into this shit and you see an first time you see an epsilon, this is right around the corner. And you're going to see an epsilon very soon. On Wednesday, you will see an epsilon. That's the other half of real analysis. So the proof. Let's start with the distance from A to C. So we've got A, B, and C, real numbers. We don't know how they sit. We don't care. We're going to work with this definition. So that's just the absolute value of A minus C, or C minus A, right? I guess that's the way I wrote it. So shit. Okay, let's just write it out like that. Whatever. Literally from the definition, right? Okay, so how do we get B in? And you've seen this trick before. There's no way you haven't seen this somewhere along the ways. We're going to insert a 0 into that statement. So watch this trick. This is equal to C, I'm going to leave a little space, minus B plus B minus A. Notice that that's just 0, but now I've got a B in there. This is the trick. And it's also kind of we're expanding our mind about what the triangle inequality says. The triangle inequality says that if I have one quantity plus another quantity, real quantity, that's less than or equal to the absolute value of those quantities. And here's where the mind expansion comes. Because this is a quantity, and this is a quantity. And I'm going to apply the triangle inequality, focusing on those as my quantity. So this is, by the triangle inequality, less than or equal to the absolute value of C minus B plus the absolute value of B minus A. What's this? What are we shooting for? What's this? Look what we're shooting for. Look what we got. What's this? Somebody tell me.
The distance of BC.
Yes, ma'am. And then Liv, what's this one here?
Distance of BA, or AB.
Yeah, absolutely. Either way. You got it either way. All good. But we're trying to make it look like the original statement. Proof done. So, triangle inequality. Make sure you write this on your page because you're going to need to think about it like this. You're rarely going to have just variable and variable. You're going to have a bunch of stuff. You need to break it apart and get an upper bound. That's what we're going to use that for, getting an upper bound on things. And we're going to know a lot about upper bounds and lower bounds. And then that's part of the art of real analysis. That's kind of all I have for you. Could you just take a minute and look at the homework problem? Just take a look at it. We got 5 minutes left, and I'm not going to see you till Wednesday. I will be in on Friday. I'm in on Friday from 12:30 to 2, and I'll probably be in tomorrow. I'll let you know when that's going to be. My Thursdays are going to be weird. I'm going to come in at different times. That's why I haven't really declared. I'm not emotionally ready to commit yet. I'm going to shut the camera. Good first week, friends.